Okay, folks, I'm Jeffrey Fox teaching this Big Data Applications Analytics course E534, 434, I523, and 423 sometimes as well. And this is part A of actually 18 parts. These are lessons which sort of chopped up in 15-minute or so sections, sometimes less than that, sometimes more. And this part is pretty straightforward. It just summarizes the other 17 parts. And it has for each of those parts a couple of sentences, so we get packed several to a slide, and then we will just go through those slides in the following part of this lesson. This lesson only has the summary of the other lessons, it has no other content. And this work is with Judy Chu and Gregor von Lesvesky. I thank them for their contributions, which have been built up over many years. We've been teaching cloud computing since, I don't know, 2008 or something, in different fashions. It was not very big in 2008, but it peaked about 4 years ago. But it's actually, if it's not no longer quite so exciting to students as a research issue, it is dominantly important and trivially overwhelmingly important in the real world. So let's knuckle down and do this. You will find some of the slides have a 2019 date on them, and this slide deck was updated from the 2019, which was a major upgrade, to 2020 just recently, October 2020. Thank you. So, all right, so we start off by defining a cloud. We give a basic definition and a couple of examples of why virtualization is important. We describe how clouds are comparable to supercomputers and high-performance computing, why multi-core underlies everything as to why clouds are so important, and we describe a typical data center and its relation to football fields. Then we get into a little more technical detail with the second lesson on defining clouds, service-oriented architectures. We built everything as a service, software as a service, platform as a service, infrastructure as a service, networks as a services. Services are just things linked by messages, or they're actually a service that you provide something which people can use. Then we look for two of the two leading public cloud providers, Amazon and Microsoft, and look at their amazing services. And then we have some general comments on clouds from Gartner. They are just the norm. I still remember lectures given, maybe 6 years ago, which were just questioning whether clouds would really make it and how long they would have to get going. Now they've not only got going, they've just overwhelmed everything. 94% of all computing will be clouds in a couple of years' time. Then we look at some of the priority matrices on infrastructure strategies. Then we look at cloud market share and how much money is being made. I mean, clouds are a win-win. The people providing clouds make money, and the people using clouds make money because they're a cheaper way of doing computing. And this tells you how important they are, why CEOs think they're important, and why Amazon is helping its other businesses through AWS. Then we go through its first key technology, virtualization, which is done through hypervisors and the various different ways you can do this. KVM, Zen, Docker, which is a container technology, and OpenStack, which is the largest open source virtualization technology. Complete system, rather complicated and too hard for actually us to use it in my research group. OpenStack is just too complicated. So then we look at the infrastructure with two lessons. We look at data center trends and their technologies. We look how they're distributed geographically, the impact on electricity, namely green computing, and also the total sizes of clouds, including an analysis by Cisco. Then in the next unit, we look at hype cycles on compute infrastructure. We compare, which is important, containers and virtual machines. That's an interesting battle which is still not quite resolved. Virtual machines are more secure, containers are faster and easier to use. And then, of course, we have AI, which is bound to be driving all of this because it's the dominant application with a lot of particularly special challenges. Other things that it can be used for, like searching in databases, but they're not particularly challenging. Then we come to cloud software, the area where I work. We introduced the Apache Big Data System, Big Data Software Stack, I should say. We look at high performance computing. We note that there are 350 software packages in this category, and they can be thought of in 21 different ways. We worship Google, who has made huge contributions here. We look at MapReduce, one of their important contributions in pictures. We compare HPC and cloud software stacks in detail, and then we look at what it takes to build a cloud or a distributed system programming environment. Then we look at applications. We start off with two lessons. Firstly, science, and then the Internet of Things, and again, different types of MapReduce, which correspond to different application structures. We use an analysis that was produced for NIST on the characteristics of applications and how they determine where they run, and we come back again to artificial intelligence. Next two sections, lessons rather, K and L, are on parallel computing, which everything uses. We describe it in pictures. We compare it with a bunch of ants and a super person and brains and things like that. We discuss a particular structure, SIMD and SPIMD, as single program multiple data or single instruction multiple data. Mostly you use SPIMD, single program multiple data. We compare big data and running large-scale simulations, such as simulating cars crashing or batteries being evolving in time, and we describe what's hard to do. The next 6 sections are particular sub-technologies within clouds. Firstly, storage, data repositories, file systems, what's called a data lake. Then we look at high-performance computing and cloud, the so-called Branscombe pyramid, from the very top of the few incredibly powerful computers to the bottom, the consumer systems, such as smartphones or laptops or desktops. And we describe supercomputers compared to clouds. We look at the difference between simulations and big data, what it implies for software and for languages. In the last page of this summary, which is the last 3 lessons here, we look at, they're called the future, but really they're just slightly leading edge, but not particularly futuristic features of clouds. Hyperscale computing, the fact that there's good to put 50,000 servers together or even more. Serverless, which means that you can instantiate everything as functions, which are just pieces of software. You don't have to worry about where they run. The cloud provider makes certain they run somewhere. Cloud native, how best to program clouds to make use of their features rather than just take your Linux cluster software and port it to clouds, which you can actually do. A key feature of cloud native is microservices, lots of tiny little parts. We divide the software up. We look at the 2019 hype cycles in this area and for cloud computing. Then we look at blockchain, which is a key security idea, and fault tolerance, which clouds have to be. Well, clouds aren't actually, but they're fault tolerant. They're not faultless. They have faults, but they have well-defined ways of coping with those faults. So that's it. Thank you. Now we get on with the actual lessons.